Dear students, today we are going to discuss the atomic models in order to study an atomic structure. So before going to study an atomic spectra, we should have the knowledge of these things. That is, what is an element and what is its composition. And we know that an electron is invented by J.J. Thomson, and discovery of positive rays, measurement of charge by Millikanson method, measurement of E by M ratio by Thomson, and mass of the electron is approximately equal to 1 divided by 2000 times that mass of an hydrogen, and distribution of positive and negative charge. So in this slide I would like to show you how the atomic spectra appears. So here you can see that there are different regions in the spectra which are consisting of distinct spectral lines which corresponds to different elements which are existing in that given compound. Okay, you will come to understand, or you will be able to account experimentally the data of spectroscopic data of the given element after getting the knowledge of atomic spectra. Okay, after completing this session, you will be able to understand that the excited atom emits light of certain wavelengths, and the emitted light can be observed as a series of colored lines with dark spaces in between. This series of colored lines is called as a line spectra or an atomic spectra, and which is a characteristic of a given element. If the atom changes, then the spectra also changes. The required prerequisites for this session is we should have the brief knowledge about the periodic table, about the elements, atoms, subatomic particles, and what is spectra and how the spectra can be obtained. So now let me start the definition of atomic spectra. Basically, it is defined as the range of characteristic frequencies of an electromagnetic radiation that are readily absorbed or emitted by an atom. It means an atomic spectra can be obtained when the light emitting substance is in an atomic state. The spectra can be obtained with the help of prism or grating, as we already know about it. The atomic spectrum is an effect of the quantized orbits of the electrons around the atom. And atomic spectra can also be analyzed to determine the composition of the object, such as stars, especially sun, which is far away from us. Now, introduction for an atomic spectra. So, introduction to the theory of atomic spectra is nothing but a systematic presentation of theory of atomic spectrum based on the modern system of a theory of angular momentum, and it is also based on the quantization of electron orbits, spin, and orientation. It also concerned with the distribution of charge as well as mass, and an atomic spectra can be considered as a fingerprint of an atom. So before going to study an atomic spectra, let us understand the different models which are proposed from time to time in order to understand the atomic structure, and they are known as atomic models. Namely, the first model is Thomson's plum pudding model, second one Rutherford's nuclear model, third one Bohr's model, fourth one Sommerfeld relativistic model, and vector atom model, as well as a wave mechanical model. So in this session, I would like to discuss the atomic models like Thomson's plum pudding model, Rutherford's nuclear model, Bohr's model, as well as a Sommerfeld relativistic model. The vector atom model we will discuss in the next session. So this is the Thomson's plum pudding model. So the picture shows the J.J. Thomson, okay, who proposed this model. He considered that an atom is a heavy sphere of diameter 10 angstrom, and according to him, positive as well as negative charges are distributed uniformly inside this sphere, and the spectral radiations which are going to be resulted is because of the simple harmonic motion of the electrons about their main positions. So these spectral radiations after emitting will be responsible to produce the spectral lines. But the theory failed to explain the results of Rutherford alpha scattering experiment. But the theory was able to explain the stability of an atom, because the electrostatic force of attraction between the two opposite charges is going to be balanced by the electrostatic force of repulsion between the two similar charges. Hence, according to J.J. Thomson, an atom as a whole is assumed to be a stable one. But he was unable to explain the large scattering of a Rutherford alpha scattering experiment. Later in 1911, Rutherford proposed a new model for an atom. According to him, all positive charges of atoms are concentrated in a very small volume at its center, and this central core he named it as a nucleus, and it is assumed to be surrounded by a cloud of electrons, which makes the entire atom electrically neutral. His model successfully explained the large scattering of alpha particles very easily, and the theory failed to explain the stability of an atom and the distribution of electrons outside the nucleus. Later, his student by name Niels Bohr developed his theory of an atomic structure by retaining the two essential features of a Rutherford's model in 1913. The atom consists of the positively charged core at its center, as well as the electrons are revolving around the nucleus in a circular orbit. By retaining these two, he assumed few more assumptions for his atomic structure. However, using Planck's quantum theory, he made the following two assumptions. The first one is the electrons can move only in those orbits for which the orbital angular momentum of an electron is equal to integral multiple of h divided by 2 pi. And second one is no energy is radiated by the electron as long as it remains in its definite or stationary orbit. The radiation of the energy takes place only when an electron jumps from one permitted orbit of higher energy to another permitted orbit of a lower energy, and the amount of energy radiated during this transition can be calculated with the help of subtracting the energies of the two successive orbits, that is E2 minus E1, which will be always equal to h into nu. But he has got certain limitations for his theory, and they are: the theory could not account the spectra of complex atoms, the theory has not given any information regarding the arrangement of electrons in an atom, and the theory also failed to explain the variation in the intensities of the spectral lines of an element, and the theory cannot be used to calculate the rate of electron transitions, and the theory failed to explain the fine structure of the spectral line. Fine structure means when each line is viewed with a high resolution spectrometer is found to be consisting of a group of lines. Hence it is known as a fine structure, as well as it is also known as a satellite. The theory failed to give a quantitative explanation for the chemical bonding, as well as the theory failed to explain the newly discovered phenomena like a Zeeman effect as well as a Stark effect. So later in 1951, to overcome these shortcomings of Bohr's theory, Sommerfeld modified his model by introducing following new ideas. And these new ideas are motion of electron in an elliptical orbit apart from the circular orbit, and considering the variation of mass with the velocity. The main features of his relativistic model are an electron moving around the nucleus described elliptical orbit in addition to circular one, and the position of electron at any time in the elliptical orbit may be fixed by two coordinates that are r as well as phi, where r is known as radius vector and phi is known as azimuthal angle. Now let us consider, according to this picture, here we have considered an electron which is nothing but a blue dot, and a red dot will indicate a nucleus, and the horizontal line will indicate the major axis, and the vertical line will indicate the minor axis of an ellipse. So here we are considering an electron of mass m moving with a linear tangential velocity v. Here the tangential velocity v can be resolved into two components, namely radial velocity, which is considered along the radius, and transverse velocity, which is considered perpendicular to the radius of the orbit. Accordingly, there exists two momentum, radial momentum as well as azimuthal momentum, where the radial momentum is directed along the radius, where azimuthal momentum is directed perpendicular to r. In addition to this, he introduced two more quantum numbers nr and n5 in order to quantize the elliptical orbits, where nr is known as radial quantum number, n5 is known as azimuthal quantum number, and we all know that n represents a principal quantum number. Here it is to be noted that the n is equal to nr plus n5. According to classical dynamics, the length of the semi-major axis is determined solely by n, while the length of the semi-minor axis depends upon n5. In case of hydrogen, the principal quantum number n is equal to 1. Then there are two possibilities. The value of nr may be equal to 0 and n5 may be equal to 1, or nr may be equal to 1 and n5 may be equal to 0. But in case of second possibility, I cannot take n5 to be equal to 0 because the whole ellipse becomes a straight line. Hence, I have to consider nr is equal to 0 and n5 is equal to 1. Hence, for n is equal to 1, hydrogen, n5 must be equal to 1. Thus, we are going to get the first orbit as a circle. Similarly, for n is equal to 2, n5 may have two values, that is 1 as well as 2. Accordingly, there exist two orbits. For n is equal to 2, n5 may be equal to 2. So therefore, we are going to get a circular orbit. And for n is equal to 2, n5 is equal to 1, which obviously gives an elliptical orbit. The figure illustrates the same. Here, for n is equal to 3, n5 may have three values, that is 1, 2 and 3. Accordingly, there exist three orbits. The same is shown in this picture, where here A represents the semi-major axis, where B represents the semi-minor axis. For n is equal to 3, if I consider n5 is equal to 3, then obviously I am going to get one circular orbit. For n is equal to 3, n5 is equal to 2, which will result an elliptical orbit. And for n is equal to 3, again n5 is equal to 1, which also result a circular orbit. So in these three orbits, one is circular and the remaining two are elliptical orbits. From the expression of energy of the orbit, we come to know that the value of n5, it depends, whatever may be the value of n5, the energies are same for all orbits with same principal quantum number. Hence, the theory failed to explain the fine structure of the spectral line. Later, by considering the variation of mass with the velocity, he would be able to explain this spectra satellite property, but he could not predict the correct number of observed fine structure of these lines. The theory failed to explain the distribution and the arrangement of electrons in atoms, and the model do not throw any light on the intensities of the spectral line. The model also failed to explain the newly discovered phenomena like star as well as a Zeeman effect. Dear students, this will complete this session, which has got summary that from this session we came to know that an atom is made up of positively charged nucleus and negatively charged electrons, where the positively charged nucleus is assumed to be situated at the center of an atom and the electrons are revolving around the nucleus in circular as well as in elliptical orbits. And it is also observed that each spectral line shows the fine structure, means every spectral line, when viewed with the help of high resolution spectrometer, they are found to be made up of number of lines. Thank you, students.